In physics, before quantum mechanics, electricity and magnetism is taught, and in that there is an equation which is called equation of continuity that relates electric charge density to the electric current density. And the same equation is used in quantum mechanics to relate not charge density, to relate probability density this time to something, and that thing is to be introduced in this lecture, and that will be given name as probability current density. So that's the whole plan. Now, if that equation, namely equation of continuity in electromagnetism, is new to you, then I can even introduce right from scratch if needed. If you know it already, you don't need it. But if you don't know, then I can remind you or maybe introduce you that if charge density, the symbol is rho, decreases in a region, that means charge is lesser in this region, and now this means the charge must go out of this region. Now the words matter. When it goes out, you can say flows out, but you better say that diverges out. And the usefulness of this word, the last word diverges, is that divergence is a term used in calculus, and that has a specific way of calculating it. So that means I repeat using that terminology. What I said is that if charge density decreases, that means its time derivative of charge density is negative. Then electric current density diverges out. That means the divergence of electric current density is positive. And remember, the first quantity is negative and the second is positive, and the net is zero, or you can say they are negative of each other. And it's the same thing. If charge density is increasing with time, that means charge is coming into this region. It's coming from outside. That means this divergence is negative. So if charge density is positive, divergence of current density is negative. Again, the same relation holds. So now that's electromagnetic theory. And now in quantum mechanics, I don't need to spend time on repeating each and everything. Most of the things are rewritten, just simply written, but I just point out the crucial differences, and there the main difference is that in case of EMT, I said charge density and I had no expression for it. It was up to your EMT course to give you an expression, but here is if that is replaced with the density, the word is preserved, but it's not charge density this time. It's a probability density. Probability density has a Born rule in quantum mechanics, that is the psi star psi wave function complex conjugate multiplied by wave function. Now rest is nothing new, but the only thing is that when charge density is related to, sorry, not charge density, this time is probability density is related to current, that will be probability current, and this is probability current, so that will flow. So otherwise you can stop and pause and see it, but I know it's all only rewritten there, so I don't have to spend time on it. And I go to the actual calculation, and that is that sorry, now before that was you continue now. Now, if probability density is psi star psi, its time derivative is the simple differentiation rule, scalar differentiation rule. This time it's just psi time derivative of psi star time derivative first derivative of second plus second derivative of first. And now you see, have you seen time derivative of wave function in quantum mechanics? And the answer is that is given in time dependent Schrodinger equation. The only thing is in time dependent Schrodinger equation, iota h bar is written here. You take to the other side, you get other side of time dependent Schrodinger equation. So time dependent Schrodinger, that's all I have written. So that will give you the red quantity in it. Now we need the blue quantity as well. So the blue quantity is just complex conjugate of that. So even if you have in the above the red you had time dependent Schrodinger equation, just same thing. It doesn't, whatever it is, you have to do the same. Take complex conjugate and that will give you this blue quantity. And now combine both red and obviously blue, which I write when needed, and you combine this in this main master equation here, first line. This is there. Psi star is written black, and this red quantity I shown you, I written here. Psi is here, and therefore in this case, if you take complex conjugate of throughout, that will become blue quantity, and that will be, you know, everything. Complex conjugate. Here also complex conjugate, iota minus iota become plus iota, and del square. You will have V star. Now, if V is real, then V star, V is potential energy. If V is real, you know, whatever, the whole plan of this lecture is valid only if potential energy is real. So you don't have V star. Psi you had star, and that's there. Now this this thing, if you know, if V terms cancels here, you say this is a multiplying, so the order doesn't matter. Psi star V psi, psi V psi star, that cancels, and you have just del square, the two quantities, and both have del square. Now that quantity is equal to minus divergence of J. It's a claim. I verify that claim later. Just furthermore listen to it. This is equal to minus divergence of J, and divergence is as defined in calculus. If J is that, now as promised, I show a verification of the last claim I made in the last minute, and that is that if J is given, and you know divergence in calculus, and even if you don't know divergence in calculus, it's like a derivative, first derivative, with some extra care which I accompany you. Now here it's also you have a product, but you should have that much care that is not a product of three things. Del is the differential operator. It's not a quantity. The quantity, when it's differentiated, then make a quantity. So it's not a product of three quantities. It's a product of two quantities indicated by two colors. And you take divergence. That is and then with slightly adopted for calculus for vector. Otherwise, it's the same product rule which I am saying. First, black. Derivative of second, sorry, that I do in the next step. For the moment, it just indicate if it's a derivative, as is derivative of first, derivative is del dot, and derivative of second. And now, sorry, what I started speaking, sorry, a bit earlier, and now I should have spoken it now. It's the first derivative of second. And as I said, it's not two quantities, second is one quantity. First, black, derivative of second, derivative is del dot, del. Plus second, and remember, the whole thing is second quantity, which is written here, and derivative of first here. And dot has to be here. That's the extra care, that's extra demand in calculus, vector calculus. The dot cannot be here because del dot cannot be of a scalar quantity. Del has to be of a scalar quantity, and that result is a vector, and that has to be taken dot product with the other quantity. And the second term is just complex conjugate of first term. So if I explain the first term, then I don't need spending time on it. You take you have four quantities, two cancel, and you are left with two quantities, and which are the same two quantities you had here. If you note, if you remember what I said maybe a few minutes ago, that V terms cancels. So that's this claim I made, that this time derivative of rho is equal to divergence of J if J is this. I have verified that claim. Now, and if in EMT this is called charge density, and that J which satisfies is called probability charge current density, sorry, in EMT. In quantum mechanics, rho is probability density and J is probability current density. And the expression is this. And now I have to, in the rest of the lecture, I have to just comment on that, but the result we have achieved. I had to introduce this quantity, I have introduced it, and I've given it a name, and that's it. Only on some comments on that. And the main comment is this quantity J, which consistency demand, we should call it probability current density, that itself is real. You know, the significance of that, I show you a calculation, maybe I first show you calculation and then I comment on it. To show if a quantity is real, the routine thing to do is that you take its complex conjugate. If it is a real quantity, then it would be equal to its complex conjugate. You take its complex conjugate, iota becomes minus iota, this thing becomes psi star, and gradient of psi star, complex conjugate of complex conjugate is no complex conjugate psi, and the same process done here. And now you take you keep iota here and take minus inside. I take minus inside here, and this becomes a minus here, and this in the second term minus becomes plus. And now you note it's the same thing. This is here and that is here. So that means this is J as before. So that means J itself is real. You know, the significance of that result is that, you know, I have already said it, that if you want to summarize whole quantum mechanics, the one you could say that the quantum mechanics is finding eigenvalues and eigenfunctions or something related accordingly of operators. You know, that is a more general statement. This includes the Schrödinger equation, because if the operator is Hamiltonian, the sentence I have spoken a moment ago, that becomes Schrödinger equation and so on. So, but one exception I have to say that, you know, the reason I said that the quantum mechanics is finding eigenvalues and eigenfunctions or an alternative to that is that eigenvalue is real. The real means measurable, and that's the signature of sign. But in terms of probability current, is not an operator, it has no eigenvalue, but it need not have eigenvalue because it itself is real, so it itself is measurable. You don't need to go to its eigenvalue. So if you make a summary of quantum mechanics, then you use operators, eigenvalues, eigenfunctions, and so on, and plus you add probability current. No eigenvalue, it itself is measurable, it's itself is real. It's called probability current density, and the way I've calculated, no, it's not necessary. I mean, this can be. I was about to say that this can be only scalar, but I have noticed I have shown gradient here, so it can be a 3 vector. So it will have a magnitude and can have direction. Direction in 3 vector x, y, z, or any combination or anything, or r theta phi, or any way of expressing direction. You know, its direction of probability current density is normally called to be direction of motion, and that's the second sense of direction of motion. Remember what earlier I said, motion in quantum mechanics. I gave you 1 minute and then I tell you. The earlier sense of motion in quantum mechanics was group velocity. So what group velocity, if it is positive or negative? If group velocity is non-zero, we say particle is moving, and the second thing is if probability current is non-zero, we say the particle is moving. So in both cases, there are the proper ways of saying it. Otherwise, there can be your imagination, or maybe other ways I am not saying. The proper ways of using the word motion in quantum mechanics are 2 written here. Now I need for next lecture an expression for probability current for a plane wave. And that I do, and that's all in this lecture I finish. And I show you calculation. Plane wave means this is an expression, this, and probability current has expression. You just combine these two pieces of information, and that means the mathematical calculation in place of psi here in the expression for probability current you substitute that thing, plane wave, and then when it is psi star, you just first take complex conjugate. These things are real, so complex conjugate will be iota replaced with minus iota, and do a calculation, and should be straightforward. Psi here, d by dx here, psi star as I explained, it's just minus iota, otherwise same. The second term is complex conjugate of first. Either you can calculate a fresh, or you just simplify the first term, and at the end you take complex conjugate of the result. Whatever way you do it, the result becomes, I show you the first term is this exponential. After differentiation, exponential remains unchanged. Only the power derivative is iota comes, and the exponential cancels the exponential. This disappears, and you are left with just what came from power, namely k, and just a star. And complex conjugate, you have it, and you do it whatever way, it's just simply, and you get that. Now here the sign is plus, so this is called right moving wave. And if you do this, repeat the calculation for k replace with minus k, the answer, in the whole calculation will be changed. Only wherever k appears, you replace with minus k, and I think it's so simple. You can redo calculation or just understand without that. Just k will be replaced with minus k, and that is expression. Probability current is negative, and that is called left moving wave. So that's I said this the second sense of motion in quantum mechanics, that I have quantified it. Okay, that's all in lecture I have to say. For conclusion, you can pause and see, but I don't take more time. Thank you very much for watching.